Okay, any questions before we get started? All right, well, so this will be hopefully the last day of me teaching y'all remote. Let me kind of pick up where we left off. Let's the field of P of n elements, the last thing that we talked about last time is actually the splitting field of this polynomial x to the P of the n minus x over the field of P elements, right? So let me kind of follow through with a couple of things about this. If you have and remember, this is over the field ZP, so we're in characteristic P here. Notice that, well, certainly this is polynomial, and notice that, of course, this polynomial is not an irreducible polynomial because, in particular, it's got a factor of x in it. Also, if you notice, 1 is also a root of this. But if you look at the derivative, since your characteristic P, the first term is P to the n, x to the P to the n minus 1, so that's 0. And the second derivative, the second one is -1. So in particular, f of x is separable. Now, what this means is in the splitting field of this polynomial, we have exactly P to the n roots. Well, let me be more precise, P to the n distinct roots. And let me just verify something. And that is, I claim, so this thing has got this glob of P to the n distinct roots. I claim that these roots form a field. Actually, they're closed under addition, multiplication, and inverses. Well, let me kind of go through this. So suppose alpha and beta are roots of this. Well, this means that alpha P to the n is alpha and beta is P to the n is beta. So if you look at well, we've actually proved before that this is alpha P to the n beta to the P to the n because we're in characteristic P, and this is alpha plus beta. So if alpha and beta are roots, so is alpha plus beta. So is alpha. Clearly, let me point out just a very minor subtlety here. Certainly alpha to the P to the n is alpha by assumption, and -1 to the P to the n is -1, even in characteristic 2. In characteristic 2, there's no distinction between 1 and -1, so this always works. So this is closed under addition. It's enclosed under additive inverses. And of course, closed under multiplication. And also, finally, point out that it's a field. So far we've got it's a ring. So this collection of roots is actually well, in fact, it's a commutative ring with identity. If alpha to p to the n is alpha, and alpha is not 0, then alpha to the minus p to the n is alpha inverse. So just by taking inverse to both of these sides, so this collection of roots is a field, and it's a field extension CP. So let me, some of you that like coding theory, number theory, and the kind of that kind of thing, let me point out here that if n equals 1, then we obtain that ZP is splitting field of and so what this means is every element of this of ZP is the root of this polynomial. And so if x is not, or if alpha say is not 0, then that means it's the root of this. Does anybody recognize this? This is kind of a beginning number theory, or sometimes I think you can do it combinatorics, but it's usually coding theory. How many of you have ever seen this? But E be a prime. Let me be careful. I'll say P is a non-zero prime. And A and Z is such that P does not divide A. Then A to the P minus 1 is equal to 1 mod P. Give me applause or a thumbs up if you've seen this before. Right, this is a famous Fermat's little theorem, right? And this follows from this observation here, because what this says is in the field of P elements, you're either 0 or your root of that polynomial. And A not divisible by P is just a statement that A is not equivalent to 0. It's not the 0 element of that field, and so it must be a root of that polynomial. So from this observation, we sort of recaptured the famous Fermat's little theorem. Let's make some more observations about this. Corollary. So here's a couple of things that I think are kind of neat. So we've already sort of talked about this a little bit. Six. For any prime p bigger than 0 and n greater than or equal to 1, there exists a field of p to the n elements and any two fields of p to the n elements are isomorphic. So let me talk through this a little bit. The existence part is just take the polynomial x to the p to the n minus x and compute a splitting field, which is just this bag of roots that makes a field. That gives the existence, right? The fact that any two of them are isomorphic is because if you have any two splitting fields of a polynomial, which these p to the n elements are, then those two fields must be isomorphic, k-isomorphic or k-space fields. And let me also point out that that's it. This is an exhaustive list because we earlier proved that if there exists a finite field, it must have exactly, or it must have p to the n elements. It has to be a prime power. Here's another corollary. For every n greater than 1, there exists an irreducible polynomial of degree n over f, where f is let me give you an example before I kind of talk my way through that one as well. So here's kind of some warm-ups to talk about this corollary. And here I say the field, and this is sort of accurate because the field of order elements. This is sort of accurate in the following sense. There's only one field of 8 elements of isomorphism, so the is sort of appropriate. Okay, so this is the splitting field. And I think last time Ernst gave us a polynomial of degree 3 that's irreducible. So because notice that the splitting field, if I call this F, and last time I asked for an example of an irreducible polynomial of degree 3, and I was given this. I want to look more in depth about this and see what's going on, because this actually, if you factor this polynomial, which is reasonably easy to do here at Ada, obviously it's more complicated as you go up, but the pattern sort of continues. Okay, I see a factor of x, and I see a factor of x minus 1. This could be a plus or a minus. because we're field characters too. Now, both x and 1 are roots of this polynomial, so that has to be a factor, right? Let's see if we can figure it out. X6, I need that, and then I need my x7 to cancel. That look right to y'all? And in fact, let me write it this way so that I don't start thinking about minuses, because there is no distinction between plus or minus in characteristic 2. So it's x8, 2x7s, 2x6, 2x5, all the way down to x. Right? Okay, so far. Now, what about that 6th degree? Well, I'm going to go ahead and factor this. That's what this one becomes. And I'm going to factor the 6th degree this way. This is the one Nancy gave us last time. This is one that we sort of noticed also had to be irreducible. Let's see if this works. I get x cubed, I get x5, and that's the only way to do it. I need an x4, so no way to, there's an x4 this way, and that's the only way to do it. There's an x cubed, and x cubed, 3x cubed is x cubed. I can get x squared this way, and that's the only way to do it. I can get x this way, and that's the only way to do it, and then I get 1. So this actually multiplies together to get this. And it's simple to check that these two are in fact irreducible because again, they're cubic polynomials over F2. And so to reduce, they have to have roots, and it's easy to check that they don't have roots in Z2. So what does this tell me? Well, there are 8 elements in the field of 8 elements. Zero element is this. 1 kills that piece, right? So these two right here correspond to the base field, C2. And 1, 2, 3, 4, 5, 6. These elements right here are the 6 extra elements that you need. Right? And notice all you need is to adjoin one of these roots, and anyone. So all you have to do is join any one of the roots of these last 2, and you will generate the entire thing. By the way, what is the multiplicative structure? Forget the 0 element. What's the multiplicative structure of the field of 8 elements? I know it's
cyclic group. Oh.
I'm sorry, what was it?
Cyclic group.
Okay, it's cyclic of order 7, agreed? Right? Because there's 8 elements in the field, then take away the 0 element, that leaves you with 7 elements. So it should be cyclic of order 7, right? Any root of either this or this has order 7. So if alpha is a root of 4, let's go with 7. Because 7 is prime, and so the cyclic group of 7 if you forget about the identity, every non-identity element must generate, it must have order 7, right? Right, in a cyclic group of order 7, you've got 6 elements of order 7 in the identity. So all these are order 7. And let me sort of show that this kind of comes full circle. So alpha is a root of that polynomial there over Z2. All right, and notice this polynomial is like that. Which, and of course, this polynomial breaks down into these two. And so this is the piece that's got 1 in it. So all the 6 ones that are non-trivial all have to have order 7. Now, of course, if you had something like the field of 16 elements, then you can do a similar thing, but it'll be a little bit more complicated because this big piece right here would have, so this is a polynomial over 6. It's x to the 7th minus 1. And so for field of 16 elements, this would be of order, polynomial would be of order 14, I guess. And it would be the 15th roots of unity. And so it would satisfy this. And so there'll be some things that have, there'll be some things that have order 15, some things that have order 5, and some things that have order 3. Okay, any questions on that? Okay. You might try to do that just for fun, is look at this, look at the x to the 16 minus x and see if you can sort of classify the elements by their orders. And this is pretty predictable. See if you can make it come full circle. Here's something else. If you have, say Z2, just for example, but actually, let's do some. The field of P elements is contained in the field P squared elements, and it's contained in the field of P cubed elements, right? But these two fields will not be common, right? Yes, I know P squared divides P cubed, but that's not really what you need. Can anybody, let me ask this question. When does what condition do you need? Anybody want to guess? For the field of P to the M elements to be contained in the field P to the N elements. Anybody want to take a stab at what condition we need on that?
If n will be a multiple of m.
Yes, that's what you need. So for example, the smallest field will contain both of these. Is the field of P to the 6 elements. What you need is M divides N. Why is that? Well, because if suppose that happens, then F Pn is a vector space over Fpn. Therefore, as a vector space, A1 to L, say, so that means field of P elements is some number of copies of the field of P to the M elements here. And now count how many elements are here. Well, the number of elements here are P M to the L power, and that must be equal to P N. Therefore, we have this necessary condition right here. And it's sufficient as well, and that's easy to check. Okay, any questions on that? Okay. Sometimes finite fields, I think this might be a little archaic, but I'm not sure. Finite fields are sometimes called Galois fields, and the following theorem kind of explains why. If K is a finite field and F is a finite extension of degree n, F and let's say that F is degree n extension of K. Then of course F is finite and Galois over K. So if you have a finite extension of a finite field K, then that finite extension is finite, which is not too surprising. And it's Galois. What is more, the Galois group F over K is cyclic. And it's for n, where n is the original degree extension. So this is one of the things that makes finite fields really, they're really symmetric, they really work out really nice. Because not only is any finite extension of finite fields Galois, right? I mean, when you're not in finite fields, we've seen very small extensions that are not Galois. Not only is Galois, the Galois group isn't just abelian, it's cyclic of order n, right? And so exercise, we'll try to see if you can figure it out. Consider for obedience. Last time. That is the function that takes any element to its p power, right? See if you can show that that should generate the Galois group. Okay. Any questions so far? Okay, so now we're going to take a little foray into cyclic extensions, cyclotomic extensions, and I'm going to talk a little bit about some stuff that leads into sort of some higher things like class field theory and things like that. We're going to look at Hilbert's theorem 90, but this is kind of a little fun foray until we kind of finish up the sort of field theory aspect of this course and kind of move on into, well, actually, my plan is to move on into arithmetic rings, but I will entertain suggestions as well. Section 8.7. And we're going to talk about radical extensions too. So last time, or the time before, when I talked about various ways to get the Galois of a polynomial, I told a story about coming up with a polynomial that wasn't solvable accidentally on the calculus test. And so, how many of you, give me a thumbs up, how many of you have kind of heard the folklore about, some polynomials are of degree too big to be solvable by radicals? How many of you have heard this? No one. Well, so those of you that haven't are in for a treat. So cyclic and cyclical atomic extensions, I also throw in radical extensions. Radical extensions are things where you get the square root. So let me kind of give you a little background. I'm going to take you back to a little history of some things I think you might have seen, but please correct me if I'm wrong. Well, first thing I know that you probably have seen. You all learned this, well, a long time ago, when you were in high school, quadratic equation. In a certain sense, it's polynomial can always be solved, but not its characteristic too. But, and let me kind of point out that, to give you an example before I go through this kind of derivation. Let me give a specific example. So look at this polynomial over Z2. It's very easy to check that it has no roots, so it's irreducible because it's quadratic. Can I solve this polynomial, or can I find the roots? Well, yes, I can, right? But you might think this is a bit of a dodge. Well, if you take f2x mod out by this ideal, then you get something that is a field extension, right? This is a PID, this is maximum ideal, so this is a field. The image of x, so if you look at the image of x in this homomorphism to, well, if you look at the homomorphism from f2x to this, the image of x is actually this root here. And so that's how I've solved it. It's just this algebraic object. It's the coset x plus this ideal. That's the root of it. You might find that unsatisfying at first, but there it is. I mean, you've got this element in this bigger field alpha that satisfies alpha squared plus alpha plus 1, 0. So in particular, alpha squared is alpha plus 1. Again, I'm ignoring the signs because it's characteristic 2. And you can make the field table. This is a field of 4 elements. And at first you might say, well, that stinks because there's no formula, but actually it's no less artificial than what I'm going to do with this, and characteristic not 2. Because what I do here, if the characteristic is not 2, then I can, if I'm hunting for roots, then I do the old hat of leading square, right? So I want to, this is a little trick to make this polynomial with a linear term here, make the linear term go away, because solving this is easy. If you allow square roots, solving this is easy. So I want to get it into that form. So I'm going to add, making this a perfect square. And here is the rub, right? I mean, this I can't pull this off if the characteristic is equal to 2. Of course, I have to have the same thing here. And so this becomes a squared minus 4b over 4. And so now I take the square root, and again, I consider this no less artificial than this construction over here, because when I say I just take the square root, what I'm saying is let alpha be a solution of x squared minus preg, right? I mean, why is that any less artificial than this? I'm just making up this thing out here. I mean, it's probably not a rational number. For example, we're over rationals, no less artificial. I take the square root of this because I think I can. I get x plus 1/2 a equals square root . If I pay attention to plus or minus because my characteristic's not 2. And again, this symbol, it's something that we've sort of grown up with, but really the symbol means this animal is a solution to the equation x squared minus whatever this blob is under the radical. So again, it's a little bit artificial. And x equals a plus or minus the square root of a squared minus 4b over 2. Or I guess that would be negative a. Right. So notice that we are able to get a solution to this in terms of what we call radicals. And this radical is a solution to x squared is something. If you have a cubic, this is more complicated, but actually you need the characteristic here to be not 3. I think you have to, yeah, and you're probably gonna have to avoid it. So you want the characteristic here to be not 2 or 3, I think. And you can reduce this by doing a changed variable, something like x minus 1/3 of a, something like this, and the 1/3 requires this. And actually, you get a formula here that involves, and if you like, I can derive that for you later, but at that point, we can go through this now. Formula involves the standard field operations. That is, the formula involves plus, minus, you know what, I'm going to give this a whirl. I think it's something close to this. I think one solution, something like x equals the cube root of let me put a question mark on that. I might have to, because I may have missed a couple of signs in here or something, but it's spiritually, it's similar to this. So there actually is a formula. So first you take this general thing, you reduce it to just a one that's missing the quadratic term. And this is very similar to completing the square, because what you do is you replace x by x minus 1/3 a, something like this. Now your burden is now shifted to solving this easier, finding a root of this easier equation, easier. And it's something like this. Now, this is a formula that involves cube root, a perfect cube root. What does this mean? Well, what does the cube root mean? It means it's a solution to something that looks like x cubed minus something. Right? And you take the cube root of Cecil, and there you go. And inside this is a square root, right? And that's a solution to x squared minus Fred, you know. And you can get this formula here. This persists up to the 4th power. And in fact, there's an equation that I have no hope of writing down off the top of my head, because it involves doing a cubic and then doing something else. It's awful. There is no general 5th degree formula. You cannot solve 5th degree polynomials in general by radicals. But I do mean in general, because, for example, we saw this in the homework. We looked at this polynomial here, and I know what one of the solutions is. Because it's already in sort of a radical form. And it turns out that all 5 solutions can be written not exactly like this, but spiritually in that form, in the sense that you're only involved with field operations, that is plus, minus, multiply, and divide, not by 0. And these perfect radicals, right? 5th root, 3rd root, square root, 4th root, whatever you need. These polynomials are called solvable radicals, and radical extensions are ones where everything can be solved, and where there's actually an interesting sort of Galois theory application to that we're going to see. We're going to talk briefly about it. I'm not going to go hardcore through the proofs on it, but I'm going to show it to you. And we're also going to look at cyclic and cyclotomic extensions. And those are very useful as well. They're very important in number theory. They're important in the theory of equations. And a very easy example that you've seen are quadratic extensions. These are cyclic extensions, because if we have where D is a square free inch. This extension is Galois. This is Galois extension. Can somebody tell me what is the Galois group? Or I'll even settle for the order of the Galois group. Anybody? Well, notice that this extension is Galois because the non-trivial automorphism takes here A and B are rational numbers, and D is my square free integer. That. And it's easy to see that the fixed field of this is exactly Q. Because if A suppose that something is fixed by this automorphism. This means that 2b radical b is equal to 0. And this means that b must be 0. But notice, again, I only come to this conclusion because the characteristic is not 2. So again, that rears its head. So this is Galois. There's only one non-trivial automorphism. So the Galois group is isomorphic to Z2. So in particular, the Galois group is cyclic, right? And when you have a cyclic Galois group, we're going to see that you get some nice extra attention. Okay, I'm going to ask you one more thing before we kind of go into this first concept that we're going to need in here, and that is the following. Here again, T is square root of 3. How many of you have ever seen this? So I want to show a hands on this. How many of you have ever seen the norm? Maybe in a number theory class. You might have had an exercise like this. If you have well, in the Gaussian integers, say. How many of you have ever seen the norm, like in an algebra class or in a number theory class? The context you might have seen it in, you might not have had Q's here, you might have had Z's here. And you might have had an exercise on figuring out the norm of this, showing things are irreducible, things like this. How many of you have ever seen this? Anybody? Okay, good, good. All right, so let me, here's something that I know you've seen. Let's have a show of hands on this. And this way I'll know how many people passed out or not. How many in your travels, maybe before undergraduate schools, ever seen something like that? Right, this is kind of the old teacher rationalizing the denominator kind of thing. What did you do to rationalize this denominator? You multiplied it by its conjugate. And that's what's going on actually here. To get this norm, to get a squared plus b squared, you multiply it by its conjugate, a minus b. Multiply it by its conjugate, a minus b radical negative 5. Right now, I'm sure that they may have used the word conjugate back in your high school days without really telling you what that meant. But the cool thing about this is when you multiply things by its conjugate, notice you get, in this case, -1, and you get 2 minus radical negative 5, or 5. So you get radical 5 minus 2. So you get rid of that nasty denominator. Notice that an element in here is a complex number, not necessarily rational. Same here, but the norms are squares, sum of 2 squares of rational numbers, a square equals 5 times the square of rational numbers. These things actually are elements of the rational numbers. So let me give you a definition and we'll wrap it for the day. Definition. Let's let F be a finite extension of K. Okay. And K bar, an algebraic closure. Okay. So it's a splitting field of all polynomials containing F. If sigma I are the distinct monomorphisms, that map F into the algebraic closure. Then we define the norm of U and F. This is the product over these embeddings, sigma I U. And this is the norm of U. And the trace to be the sum. Sum I equals 1 M of sigma I. So this is what we call the norm and the trace, and we'll talk about this in detail next time. Any questions? Any questions at all? All right, well, if all planes run on time, I will be back Friday, just like regular. Until then, we will see you all later.